Let's go to idea one, the big idea. Jensen's formula is about a hidden connection between the inside of a circle and the outside edge of that circle. Inside the circle, there are special points called zeros. A zero is a place where the function becomes zero. These zeros are hidden inside the disk, but on the outside edge, we can measure the size of the function all the way around. So the question is this: can the outside edge tell us something about the hidden zeros inside? Jensen's formula says yes. The outside edge remembers what is happening inside. The zeros leave a fingerprint on the boundary. That is the whole mystery. Hidden zeros inside, measurable behavior outside, and Jensen's formula connecting the two. Let's go to idea two, the setup. We begin with a function inside a disk in the complex plane. Picture the disk as a filled-in circle. The center is zero. The radius is called the radius. Every point inside the disk is closer to the center than the radius. Every point on the boundary is exactly one radius away from the center. The function has to behave nicely inside the disk. In complex analysis, that means the function is analytic. For this video, think of analytic as meaning smooth, rigid, and deeply connected. The values of an analytic function are not random. What happens inside affects what happens around the outside. We also assume the function does not equal zero at the center. That prevents the center measurement from breaking. So the setup is simple: a nice complex function, a disk, some hidden zeros inside, and a boundary circle around everything. Let's go to idea three. Why the boundary? Why do we measure on the outside edge? Why not measure on some smaller curve inside the disk? The answer is a closed curve only detects the zeros it surrounds. If you draw a small circle inside the disk, that small circle only surrounds part of the region. It only sees the zeros inside that smaller circle. It misses the zeros outside that small circle. But the outer boundary surrounds the whole disk, so the outer boundary sees the whole interior story. That is why Jensen's formula uses the boundary circle. The boundary is the complete enclosing loop. It is like placing a detector around the entire region. Everything inside leaves its total effect on that outer loop. Let's go to idea four, walking around the outside edge. Now imagine walking around the boundary circle. At every angle, you stop and measure the size of the function. Do not worry about the exact complex notation yet. The important idea is this: each angle gives one boundary point, and each boundary point gives one measurement. The measurement is not the function itself. The measurement is the log of the size of the function. So as you walk around the circle, you collect many values. Some are high, some are low, some are low, some may dip near places influenced by zeros. together form boundary data. Then Jensen's formula averages them. So the entire outside edge gets compressed into one number, the average log size of the function around the boundary. That number is not random. It carries information about what is hidden inside. Let's go to idea 5. Why take the log? This is the key move. Zeros are naturally connected to multiplication. A function with zeros can be thought of as a smooth part multiplied by zero factors. Here is the spoken version. The function equals a smooth part times the factor connected to the first zero times the factor connected to the second zero times the factor connected to the third zero, and so on. Each zero has its own factor, but multiplication tangles all those factors together. The first zero, second zero, and third zero are all mixed into one product that is hard to read. The log fixes this. The log turns multiplication into addition. So after taking the log, the product becomes a sum. The smooth part gets one term, the first zero gets one term, the second zero gets one term, the third zero gets one term, and so on. That is why the log is used. The log takes a tangled product and turns it into separate add-ons with.
Let's go to idea 6, the center value. Jensen's formula begins with the measurement at the center. The center is the point 0. At the center we measure the log of the size of the function. In spoken language, take the function at the center, take its size, then take the log that gives the center value. The center value is the starting point of the inside story. If there were no zeros inside, the center value would already be closely connected to the average around the boundary. That is one of the beautiful things about analytic functions. Their center behavior and their circular average are deeply linked. But zeros change the story. Zeros add extra corrections. So Jensen's formula begins with the center value, then adds the zero contribution. Center value first zero, add on second boundary average at the end. Let's go to idea 7. 1 0 1 add-on. Now focus on just 1 0. Suppose 1 0 sits somewhere inside the disk. That 0 has a distance from the center. Jensen's formula says the contribution of that 0 depends on how far it is from the center compared with the radius of the disk. Here is the plain version. Take the radius of the disk divided by the distance of the 0 from the center. Then take the log, that is the add-on, from that 1 0. If the 0 is close to the center, its distance from the center is small. So the radius divided by that small distance is large. The log of a large number is larger. So a 0 near the center contributes a lot. But if the 0 is close to the boundary, its distance from the center is almost the same as the radius. So the radius divided by that distance is close to 1. The log of something close to 1 is close to 0. So a 0 near the boundary contributes much less. That is the visual meaning. Closer to the center, bigger add-on. Closer to the boundary, smaller add-on. If a 0 repeats, we count its contribution again. A double 0 gets counted twice. A triple 0 gets counted 3 times. Let's go to idea 8, building the inside side. Now we build the inside side of the formula. Start with the
the center value.
That means take the function at the center,
Take its side.
then take the log. After that, add the contribution from every zero inside the disk.
For each zero,
Look at its distance from the center. Compare that distance to the radius
of the disk.
Take the log of that ratio.
Add the result.
So the inside side
Is center value.
plus the first zeros add
Plus
on,
the second zeros add on.
plus the third zeros add on.
And so on.
This is the discrete side of Jensen's formula. Discrete means the zeros come as separate points.
1 point, another point.
Another point. Each one adds its own contribution. Then let's go to idea 9.
The boundary side.
And the full balance.
Now look at the boundary side.
The boundary side is continuous. That means we are not adding separate interior points. We are measuring all the way around the outside circle. Every angle contributes. Every boundary point contributes. At each point on the boundary, we measure the log of the size of the function. Then we average all those measurements. That gives one number, the average log size around the boundary. Now the full balance appears. The inside side says
Center value.
plus all the zero
The
add-ons.
boundary side says
Average log size around the outside circle.
Jensen's formula says
These two sides are equal. That means the boundary average is not just an outside measurement. It contains information about the interior zeros. Let's go to idea 10.
what Jensen really reveals.
Jensen's formula is not just a formula to memorize.
It is a way of seeing.
It says, if you know how the size of a complex function behaves around a boundary, then you can learn something about the zeros hidden inside. The boundary acts like an enclosing detector. The log separates the hidden multiplicative pieces.
The center value gives the starting measurement.
Each zero adds a correction based on its distance from the center. And the average around the boundary balances the whole story. That is the deep message. The outside edge is not separate from the inside.
For analytic functions,
The boundary reveals the interior.
hidden zeros inside become readable through the average behavior on the boundary. That is Jensen.